Hello friends, you are watching channel number Collage. This is my sincere effort to help you understand basic mathematics in a simple and easy manner. In this video, we will understand what is a scalar triple product. Scalar triple product is useful in finding the volume of a parallelepiped and a tetrahedron whose coterminous edges are represented by three vectors a bar, b bar and c bar. It is also useful in deciding the coplanarity of three vectors a bar, b bar and c bar. To understand scalar triple product, we will consider three vectors a bar equals a1i plus a2j plus a3k, b bar equals b1i plus b2j plus b3k, c bar equals c1i plus c2j plus c3k. We know that dot product or scalar product of a bar and b bar is a1 b1 plus a2 b2 plus a3 b3, which is sum of the product of corresponding coefficients of I, j and k. We also know the vector or cross product of b bar and c bar, which is a determinant in I, j, k, b1 b2 b3 c1 c2 c3, which is a vector b bar cross c bar given as b2 c3 minus b3 c2 I minus b1 c3 minus b3 c1 j plus b1 c2 minus b2 c1 k. Now we will define scalar triple product of three vectors a bar, b bar, c bar. Scalar triple product is also known as box product and it is written as box a bar, b bar, c bar. Box a bar, b bar, c bar is defined as a bar dot b bar cross c bar. You will observe that this is a dot product of vector a and a vector obtained by the cross product of b bar and c bar. Now we have already obtained the cross product of b bar and c bar as this vector. Now we will write box a bar, b bar, c bar as a bar dot b bar cross c bar. We will write a bar as a1i plus a2j plus a3k and b bar cross c bar, which we have already obtained here, we will write over here. Now we know that dot product of two vectors is nothing but the sum of the product of the corresponding coefficients of I, j, k. So first we will write coefficient of I here, which is a1, and the corresponding coefficient of I over here, which is b2c3 minus b3c1. Next we write coefficient of j, which is a2, and corresponding coefficient of j, which is b1c3 minus b3c1 here, plus we write coefficient of k, which is a3 here, and corresponding coefficient of k here, which is b1c2 minus b2c1 here. Now this right hand side can also be written in the form of a determinant, which will be a1 a2 a3 b1 b2 b3 and c1 c2 c3. So box a bar, b bar, c bar is nothing but a determinant in a1 a2 a3 b1 b2 b3 and c1 c2 c3. Let us understand the properties of scalar triple product. The first property is box a bar, b bar, c bar is same as box b bar, c bar, a bar, which is same as box c bar, a bar, b bar. Here we have made a cyclic change in the order of vectors a bar, b bar, c bar. Here b bar is followed by c bar is followed by a bar, which is a cyclic change. Here c bar is followed by a bar and a bar is followed by b bar, which is also a cyclic change. Second property, box a bar, b bar, c bar by definition is a bar dot b bar cross c bar, which can also be written as a bar cross b bar dot a bar, which means that if we change the order of dot and cross, the value of the box product does not change. Here dot has been replaced by cross and cross has been replaced by dot. Third property, box a bar, b bar, c bar equals minus b bar, a bar, c bar, because we have made a single change in the order of a bar and b bar, which is same as minus c bar, b bar, a bar. Here also we have made a single change in the order of a bar and c bar, which is same as minus box a bar, c bar, b bar. Here also we have made a single change in the order of b bar and c bar. Therefore, when we make a single change in the order of the three vectors, the value of the box product changes its sign. Fourth property, box 0 vector b bar c bar is same as box a bar 0 vector c bar is same as box a bar b bar 0 vector, which is equal to 0, which means that if any of the three vectors is a 0 vector, then the value of the box product is 0. Fifth property, box a bar b bar c bar is 0 if any of the two vectors are collinear, which means that any of these two vectors can be expressed as a non-zero scalar multiple of the other. Sixth one, box a bar b bar c bar is 0 if the three vectors are coplanar, which means that any one of these three vectors can be expressed as a linear combination of the remaining two. Now that we have understood the concept of scalar triple product and its properties, we will solve some examples on it. So the first question is, we have to find box a bar b bar c bar, where a bar is 3i minus j plus 4k, b bar is 2i plus 3j minus k, c bar is minus 5u plus 2j plus 3k. We have box a bar b bar c bar equals a1 a2 a3 b1 b2 b3 c1 c2 c3. We will solve this determinant. It will be 3 times 9 plus 2, minus of minus 1 will be plus 1, 6 minus 5 plus 4 times 4 plus 15. So it will be 11 3s are 33, this will be 1, and 19 4s are 76. So the box product a bar b bar c bar works out to be 110. We will see volume of a parallelepiped with coterminous edges a bar b bar c bar. As a scalar triple product of vectors a bar b bar c bar. First we will draw AP perpendicular to parallelogram OCDB. AP perpendicular to parallelogram OCDB. Let angle OAP equals theta degrees. This angle. Height of the parallelepiped AP will be mod A bar cos theta. We have learned that area of parallelogram OCDB equals mod B bar cross C bar. Volume of parallelepiped is given as area of parallelogram OCDB, which is the area of the base parallelogram, multiplied by height of the parallelepiped AP. Area of parallelogram OCDB is mod B bar cross C bar, which we write here, and height AP is mod A bar cos theta, which we write here. We will rewrite this as mod A bar into mod B bar cross C bar cos theta. This is nothing but A bar dot B bar cross C bar, because we know that mod A bar into mod B bar cos theta equals A bar dot B bar. Therefore, mod A bar into mod B bar cross C bar cos theta will be A bar dot B bar cross C bar, which is nothing but scalar triple product of A bar, B bar, C bar. Thus, we find that volume of parallelepiped with coterminous edges A bar, B bar, C bar is a scalar triple product of vectors A bar, B bar, C bar. In the first question, we have to find the volume of the parallelepiped whose coterminous edges are A bar equals 3i cap plus 5k, B bar equals 4i plus 2j minus 3k, C bar equals 3i plus j plus 4k. Volume of the parallelepiped is given as A bar dot B bar cross C bar, which is given as a determinant A1 A2 A3 B1 B2 B3 C1 C2 C3, which will be 305 4 2 minus 3 314. That gives us 3 times 4 2s are 8 plus 3 minus 0 times 16 plus 9 plus 5 times 4 minus 6. It will be 11 3s are 33 minus 0 minus 2 5s are minus 10. So this gives us volume of the parallelepiped as 23 cubic units. In the second example, we have to find volume of the parallelepiped whose coterminous edges have been given as A bar equals minus 2i plus 3j plus k, B bar equals 4j, C bar equals minus I plus 3j plus 3k. Volume of the parallelepiped is given as A bar dot B bar cross C bar, which will be a determinant of A1 A2 A3 B1 B2 B3 C1 C2 C3, which will be minus 2 3 1 0 4 0 minus 1 3 3. It will be minus 2 times 12 plus 0 minus 3 times 0 plus 0 plus 1 times 0 plus 4. It will be 12 multiplied by minus 2 minus 24 minus 0 and plus 4, which will be minus 20. Here the volume of the parallelepiped is negative, but we have to consider its absolute value. Therefore, volume of the parallelepiped will be 20 cubic units. We will see how volume of a tetrahedron with coterminous edges OA bar equals A bar, OB bar equals B bar, and OC bar equals C bar will be the scalar triple product or the box product of the three vectors A bar, B bar, C bar. First, let us draw height Cn, which we call H, perpendicular to base triangle OAB. So we draw this Cn, which is perpendicular to this base triangle OAB. Now it will be mod C bar cos theta. We know that area of triangle OAB is half mod A bar cross B bar. Volume of tetrahedron is given as 1/3 area of base triangle OAB multiplied by height h. Now area of triangle OAB is half mod A bar cross B bar, which we write here, multiplied by h. We have h equals mod C bar cos theta, which we write over here. So this will be 1/6 mod A bar cross B bar dot mod C bar cos theta, which is nothing but 1/6 A bar cross B bar dot C bar, which is scalar triple product of vectors A bar, B bar, C bar, or it is 1/6 the box product of A bar, B bar, C bar. Thus, we see that volume of a tetrahedron with coterminous edges A bar, B bar, C bar is 1/6 of the scalar triple product or the box product of vectors A bar, B bar, C bar. In the first question, we have to find the volume of the tetrahedron, which is shown over here, whose vertices are A -1, 2, 3, B 3, -2, 1, C 2, 1, 3, and D -1, -2, 4. From the coordinates of these vertices, let us first write their position vectors. So, position vector of vertex A will be A bar equals -I plus 2j plus 3k. That of B will be 3I minus 2j plus k. Of C will be 2I plus j plus 3k. And D will be -I minus 2j plus 4k. These position vectors have been written from their corresponding coordinates. Let us find AB bar, which will be B bar minus A bar. So here it is B bar minus A bar. It will be 3 plus 1, that is 4I, minus 2 minus 2, that will be minus 4j, and 1 minus 3, that will be minus 2k. Then AC bar will be C bar minus A bar. This is C bar. This is A bar. It will be 2 plus 1, that is 3I, 1 minus 2, that will be minus j, and 3 minus 3, that will be 0k. And AD bar will be D bar minus A bar, which will be, this is D bar minus this is A bar. So it will be minus 1 plus 1, that is 0i, minus 2 minus 2, that will be minus 4j, and 4 minus 3, that will be k. The coterminous edges of this tetrahedron are represented by vector AB bar, which is 4i minus 4j minus 2k, AC bar, which is 3i minus j, and AD bar minus 4j plus k. Therefore, the volume of this tetrahedron will be 1/6 time AB bar cross AC bar dot AD bar, which is given as 1/6 times A1 A2 A3 B1 B2 B3 C1 C2 C3, which will be 1/6 times 4 minus 4 minus 2, 3 minus 1 0, and 0 minus 4 1, which will be 1/6 times 4 times minus 1 minus 0, minus of minus 4, that is 4 times 3 minus 0, and minus 2 times minus 12 minus 0. So it will be 1/6 times, this will be minus 4, this will be 12, and this will be 24. So we get 1/6 multiplied by 32, which will be 16 by 3 cubic units, which is the volume of this tetrahedron. In the second question, we have to show that the volume of this tetrahedron, whose coterminous edges are 7i plus k, 2i plus 5j minus 3k, 4i plus 3j plus k, is 14 cubic units. First, we will represent the given vectors by A bar equals 7i plus k, which is the first coterminous edge, B bar equals 2i plus 5j minus 3k, which is the second coterminous edge, and C bar equals 4i plus 3j plus k, which is the third coterminous edge. Now that we know the coterminus represented by these vectors, we will write the volume of the tetrahedron as 1/6 times A bar cross B bar dot C bar, which will be 1/6 the determinant A1 A2 A3 B1 B2 B3 C1 C2 C3, that is 1/6 times 701 25 minus 3 431, which will be 1/6 times 7 times 5 plus 9 plus 0 times 2 plus 12 plus 1 times 6 minus 20. This will be 14 sevens are 98, this will be 0, this will be minus 14. So it will be 1/6 times 84, which is 14 cubic units. Therefore, it is proved that the volume of this tetrahedron, whose coterminous edges are A bar, B bar, C bar, is 14 cubic units. To understand coplanarity of vectors, we have to consider scalar triple product. We have seen that the scalar triple product A bar dot B bar cross C bar represents the volumes of the solids such as parallelepiped and tetrahedron, whose coterminous edges A bar B bar C bar and are essentially non-coplanar. Now imagine if the volume of these solids is 0, then the scalar triple product A bar dot B bar cross C bar will be 0, which will mean that the vectors A bar B bar C bar will no longer remain non-coplanar, they will be coplanar. Therefore, the scalar triple product A bar dot B bar cross C bar equals 0 is essential and sufficient condition for the vectors A bar B bar C bar to be coplanar. In the first question, we have to show that vectors I minus j minus 6k, I minus 3j plus 4k and 2i minus 5j plus 3k are coplanar vectors. First, we will name these vectors. We will call A bar I minus j minus 6k, B bar I minus 3j plus 4k, C bar 2i minus 5j plus 3k. We will take their scalar triple product and write A bar dot B bar cross C bar, which will be a determinant 1 minus 1 minus 6, 1 minus 3 4, 2 minus 5 3. We will evaluate this determinant and write 1 minus 9 plus 20, this 1, this 3 minus 8, this minus 6 minus 5 and plus 6. So this gives us, this will be 11, this will be minus 5 and this will be minus 6. So 11 minus 11 will be 0. So the scalar triple product A bar dot B bar cross C bar equals 0. Since the scalar triple product of A bar B bar C bar is 0, we conclude that the given vectors are coplanar vectors. If you have understood the concept of scalar triple product and problems based on that, please like this video, subscribe this channel to get more videos of this type, share this video with your friends and relatives. Thanks for watching. See you in the next video. Keep watching Number Collage. Thank you.